Hello everyone, this is lecture 14, partial derivatives. So the derivative of function of one variable y equal to f of x measures the rate of change of y with respect to x, and it gives slopes of tangent lines. The analogous idea for functions of several variables presents a new twist. Derivatives may be defined with respect to any of the independent variables. For example, we can compute the derivative of the function f of x, y with respect to x or with respect to y. The resulting derivatives are called partial derivative. They still represent the rate of change and they are associated with slope of tangents. Therefore, much of what you have learned about derivatives applies to functions of several variables. So that's the idea of this lecture, and hopefully at the end of this lecture, you would be able to calculate partial derivative of function of two variables or more, and determine the higher order derivative of function of two variables. Before I present the formula to find the derivative of function of two variables, I want to go back to the limit definitions of derivative of functions of one variable. So that is, consider the function of a single variable of the form y equal to f of x. The limit definition of derivative of the function is written as f prime of x equal to the limit of f of x plus h minus f of x divided by h as h approaches 0. So that is the limit definitions of derivative of functions of one variable. Now for derivatives of two variables, so consider a function f defined on the domain D in the xy plane. Suppose f represents the elevations of the lane above sea level over D, which is again the domain of the functions. Imagine that you are on the surface z equal to f of xy at the point a, b, f of ab, and you are asked to determine the slope of the surface where you are standing. Your answer should be, it depends. So let's take a look at the following figure. So this figure shows a function that resembles the landscape in this figure. Suppose that you are standing at the point p equal to 0, 0, f of 0, 0, which lie on the saddle. So the surface behaves differently depending on the direction in which you walk. If you walk east, which is in the positive x directions, the elevations increases and your path takes you upward on the surface. If you walk north, which is on the positive y directions, the elevation decreases and your path takes you downward on the surface. In fact, in every direction you walk from the point P, the function value change at different rates. So how should the slope or the rate of change at a given point be defined? So the answer to this question involves something called partial derivative, which arises when you hold all but one independent variable fixed and then compute an ordinary derivative with respect to the remaining variable. So that is, by definition, let f of x, y be a function of two variables. Then the partial derivative of f with respect to x is written as, you have partial f, partial x. So this is the notations for partial derivative of the function f with respect to x. In the regular derivative, you have d dx. So for partial derivative, we're going to use these following notations. So this is called partial x to say that we're going to take the partial derivative of a function with respect to x. There is another notations that you can use, which is f with the subscript x to indicate that let's take the first partial derivative of the function with respect to x. So in this case, what you do is that you're going to fix the variable y and you're going to take the derivative with respect to x only. And together with the limit definitions of derivative that you see earlier right here, you're going to modify this formula so that you can arrive at the partial derivative of the function with respect to x. That is, this is equal to the limit of f of x plus h, y. In this case, we're going to fix the value of y and just going to do with x only, minus f of x, y, altogether divided by h as h approaches 0. Now similarly, the partial derivative of f with respect to y, can you fix this for me please, is given as, so again the notation is partial f, partial y, to indicate that you want to find the partial derivative of the function f with respect to the variable y. There is another notation that you can use, that is f sub y, again to indicate that you want to find the first partial derivative of the function with respect to y. In this case, you want to fix the value of x and you're going to work with y only. So in this case, you have the limit of the functions f of x, y plus k minus f of x, y divided by k for k approaches 0. So in this case, h and k are just some small distance. It's just a dummy variable. You can just switch to another letter if you like. You can also keep this one as h if you like. It doesn't matter. It's just I want to present it in a way that so that you can see the difference between the partial derivative of the function with respect to x and the partial derivative of f with respect to y. Now, so that is the limit definitions of the partial derivatives. In practice, so to find the derivative, so to find partial f, partial x, or f sub x, what you do is you let y be a constant. That is, you fix the value of y and then you differentiate the function with respect to x only. And differentiates f of x comma y with respect to, so WRT means with respect to x only. Now similarly, when you want to find partial f, partial y, or f sub y, what you do is you let x be a constant and you differentiate f of x comma y with respect to y only. Again, WRT means with respect to. So basically that is the definitions of partial derivative of a function with respect to the variable x and the partial derivative of the function with respect to the variable y. Now let's take a look at the following example. So let's consider the following functions of the form f of xy equal to x squared y plus 5 times y cubed. You want to find the partial derivative of the function with respect to x and the partial derivative of the function with respect to y. So when you want to find f sub x or partial f, partial x, what you do is you let y equal to a constant. So in this context of finding partial derivative with respect to x, y is a constant. So 5y cubed in this case is going to be a constant. So I'm going to do partial x of x squared y plus 5y cubed. Again, remember you take the partial derivative of the function with respect to x. So y is a constant. 5 times y cubed is also a constant. So basically you just take the derivative of x squared. So the derivative of x squared is 2x, as you know from the single variable calculus. So you're going to get 2x times y plus the partial derivative of x with respect to 5y cubed. And again, 5y cubed in this context is a constant, so therefore the derivative of 5y cubed with respect to x is going to be equal to 0. So you only have 2xy as the answer. Now, if you move on to find the partial derivative of the function with respect to y, or partial f, partial y, you're going to treat x as a constant in this context. So x squared is a constant. You're just going to take the derivative of y only, plus 5y cubed. So in this case, 5y cubed is no longer a constant. You need to take the derivative with respect to y for this particular function. So the derivative of y is 1. So you have x squared times 1. Plus the derivative of 5y cubed, that is 5 times y cubed, that is 3 times y squared, right? Because the derivative of y cubed is 3y squared. And you simplify the answer and you get x squared plus 15y squared. So as you can see, when taking the partial derivative with respect to x and with respect to y, you have a different answer. For the next example, in example 2, you want to find the partial derivative with respect to x and partial derivative with respect to y of the function f of x comma y equal to e to the xy. So f sub x is equal to partial f, partial x, or this is partial x of e to the xy. Again, in this context, y is a constant and x is the variable that you need to take the derivative on. When you take the derivative of this function, you need to apply chain rule. So you get the derivative of the outside function, which is an exponential function. Right? To see that type of chain rule, it's good to rewrite this function e to the xy as exp of xy. When you rewrite the exponential function in terms of exp of x times y, it's easy to see that the exponential function is the outside function and x times y is the inside functions. So you're going to take the derivative of the outside function, that is still e to the x times y. Then you multiply with the partial derivative with respect to x of the inside function. In this case, the inside function is x times y. And the partial derivative of x times y, again, y is a constant in this context. Therefore, the partial derivative of x times y is just y. So you get e to the xy times y. Now for f sub y, or partial f, you got the partial derivative of e to the xy with respect to y. In this context, x is a constant. And again, if you rewrite e to the x times y at exp of x times y, you're going to see that exp, which is the exponential function, is the outside function, and the product x times y is a inside function. So the derivative of the outside function, the exponential function, is still e to the x times y times the partial derivative of the inside function with respect to y. Again, in this context, x is a constant, and the derivative of x times y is just x. So you have e to the xy times x. Alright. Again, the partial derivative with respect to x and the partial derivative with respect to y will produce different results. In example 3, you have the function of the form f of xy equal to x to the a times e to the y. When you take the partial derivative with respect to x, you have partial f partial x. This is equal to partial x of x to the a times e to the y. So in the context of finding partial derivative with respect to x, y is a constant, therefore e to the y is also a constant. That is, you can pull e to the y out of the derivative operation. That is e to the y times partial x of x to the 8. So you take the derivative with respect to x of x to the 8, you're going to get e to the y times 8 times x to the 7. Or you can rewrite this as 8 times x to the 7 times e to the y. Similarly, for the case of f sub y or partial f partial y, you got partial y of x to the 8 times e to the y. In this context, x is a constant. Therefore, x to the 8 is also a constant, and you can pull that out of the derivative operations. That is x to the 8 times partial y of e to the y. So the partial derivative of e to the y with respect to y is just e to the y. So you got x to the 8 times e to the y as the answer. Now moving on to example 4. You have the function of the form x cubed plus x squared times y cubed minus 2 times y squared. And you want to find the partial derivative of the function with respect to x and the partial derivative of the function with respect to y. And then you want to evaluate the partial derivative with respect to x at the point 2, 1, and evaluate the partial derivative of the function with respect to y at the point 2, 1. So let's find the partial derivative first. So you get f sub x equal to partial f partial x partial x of x cubed plus x squared y cubed minus 2y squared. Again, in this context of finding partial derivative with respect to x, y is a constant. Therefore, y cubed is a constant, negative 2y squared is also a constant. So the partial derivative of x cubed is 3x squared plus partial derivative of x squared times y cubed is equal to 2x times y cubed, and the partial derivative of this constant is equal to 0. So you have this plus 0. Right. So what we did here is that the derivative of a sum is sum of derivatives. Derivative of difference is difference of derivatives. Right? Those are law or rules you have seen in single variable calculus, and you can directly apply here in the context of partial derivatives. And the result is just 3x squared plus 2x times y cubed, and you can get rid of 0 here if you want to. Now for f sub y, so partial derivative of the function with respect to y, or partial f partial y, you get partial y of x cubed plus x squared y cubed minus 2y squared. In this context, x is a constant, therefore x cubed is also a constant, and x squared is a constant. So the partial derivative of x cubed with respect to y is equal to 0. Plus, so x squared in this context is a constant multiple, and you just do x squared times the partial derivative of y cubed, that is 3 times y squared, and partial derivative of negative 2y squared with respect to y will give you minus 2 times 2y. And you simplify the result, and you're going to get this is 3x squared y squared minus 4y. So this result are just the partial derivative with respect to x and with respect to y. Now you need to evaluate the partial derivative at a given point 2, 1. I'm going to evaluate the result of the partial derivative at the point 2, 1. So you get f sub x of 2, 1. There's another way to write this notation as partial f partial x with a big vertical line of 2, 1 indicate that You want to evaluate the partial derivative of the function with respect to x at the point 2, 1, that is x equal to 2 and y equal to 1. And you get this is equal to 3 times 2 squared plus 2 times 2 times 1 cubed, and the answer should be 16. Now, similarly, you want to evaluate the partial derivative of the functions with respect to y at the point 2, 1. You can write this as f sub y of 2, 1. This is equal to partial f partial y. Evaluate at 2, 1. And this is equal to 3 times 2 squared. Again, x is equal to 2, y is equal to 1. 1 squared minus 4 times 1. And you're going to get this to be equal to 8. Alright, so hopefully this example gives you the idea how to calculate partial or the first partial derivative with respect to x and the first partial derivative with respect to y, as well as the evaluations of partial derivatives at the given points.